Good morning, everyone. So I'm Julian. Today I'm going to talk about Apache Parquet and Apache Arrow, how they work and how they integrate. So I'm a principal engineer at WeWork working on the data platform. I'm one of the co-creators of Parquet a few years ago. I'm an Apache member. I've been involved in a bunch of Apache projects over the years. Used Hadoop first at Yahoo in 2007. Formerly at Twitter, and anybody knows that guy? This is King Julian from the movie Madagascar, so we share the same first name. I won't do the dance, though. So today, I'm going to start with talking about community-driven standards and open source and communities. And I think that's a very key part of the open source. Second, then I'll start talking about the benefit of columnar representation, what we get from that. And then I'll go through the vertical integration between Parquet and Arrow, and I'll get in the details of what I mean by that. And then I'll give some elements about Arrow-based communication, how it benefits the ecosystem. So first, let's talk about community-driven standard. So you know, when Parquet started, there was a common need for an on-disk columnar format in the Hadoop open source ecosystem. And I was prototyping something on my side. It was not called Parquet yet. The Impala team at Cloudera was prototyping something. And obviously, there have been like a couple other initiatives that were happening also. So there was this need, and we started like talking to each other, putting those efforts together. And Parquet came of that collaboration between me at Twitter and the Impala team. And you know, the idea was not just to improve the technology and have something proprietary, right? That would have been that useful. The goal was also to define that as an open project, open standard that everybody could use, and then you can benefit from all those integrations that are happening in the ecosystem. You don't have to implement yourself all those integrations with all those systems. So Arrow has been coming from this same common need for an in-memory columnar representation. And I will go through why, you know, why it's not exactly the same, why we don't just put Parquet in memory. But Arrow is benefiting that over the year, we've been building that community around Parquet, right? So we started with like 2 main contributors, and then other companies, other contributors came around like Criteo and a bunch of others. The Drill project, Spark started using it. All those projects started using Parquet, and so we built that community, and already all those projects were talking to each other around like kind of, hey, what features do we need from that? How do we merge all those features in one project? And so Arrow is benefiting from that, and so we started this Arrow project by putting a lot of people from those various projects in the same room and saying, hey, this is a kickstart. We need to standardize these representations so that we can benefit from it being a standard and not every team doing its own thing, like it was starting to happen. And from there's been some iteration, agreeing on what the feature should be, what the focus on the project, standardizing types and representation, and from there you can start parallelizing the adoption of the project. And there's a lot of work in integrating it in a bunch of things. So because if you think of, you know, initially, for example, Parquet, everybody, to get good performance, every of those query engine or processing project needs to integrate deeply with Parquet to be very performant and take full advantage of it. So there's some duplication of effort. And also whenever you need to integrate those things, like you read data from any of those storage layer, you need to re-implement, find a common on-wire representation, convert from the in-memory representation to another if you exchange data, and there's a lot of waste happening, right? A lot of CPU is wasting on serialization, deserialization, converting from one representation to another. Often those representations are just the lowest common denominator, and that creates a lot of friction in the work that need to be done, and also a lot of ineffective, a lot of CPU wasted. So the idea with Arrow is to agree on a common efficient for data processing in-memory representation, but at the same time agree on a common standard so that when we exchange that data, it's done once, and we don't have to convert from one to the other. And there can be a lot of common effort on, hey, how do you load Parquet into Arrow? And then that's shared with everyone instead of everyone figuring out how to convert Parquet, load it into their own internal in-memory representation. So there are two main benefits, like sharing work and having a common shared zero cost to convert in-memory format. So now I'll talk a little bit of those two things are Columnar. So benefits of Columnar. This slide is supposed to be self-explanatory, right? Row-oriented, column-oriented. Everybody's getting it? So joke apart, aside, everybody has this two-dimensional representation of a table in mind. But really, memory, whether it's disk, is SSD, it's RAM, it's linear, right? It's one-dimensional. So you need to pick whether you're going to write the data row by row, so that's a traditional row layout, or column by column, right? So either you go like this, right, or you go like this. And so that's the main difference between row and columnar. So row is more straightforward, right? You'd have one row after the other. So if you're filtering on something, you can evaluate an expression on a row, go to the next one, and so on. And column is the other way around. So the benefits of the columnar layout is, one, you can encode a bunch of values of the same time together. So you can have much more efficient and smarter encodings. And also compression works better because when things are more homogeneous. When you have row layout, because you have different types and they can have different widths, you kind of have forced to align things on byte boundaries, and you have more constraints on how you store the data. And also, it's very heterogeneous, right? You may have like a name, a number, a decimal, different things, and then you apply compression on top of it. It's less efficient than it works on a bunch of things of the same type. And also, when you're accessing data, usually when you do query on the data set, you may have hundreds of columns, but you're querying on a few of them, right? Maybe you select A where B equals something. So in a columnar layout, it's really easy and efficient to skip entire column because you read one column, you skip this, you seek to the next location, and then you read that one. If you want to do the same thing in a row layout, you have a bunch of small seeks and a lot of small jumps that are actually a lot less efficient than doing big scans and reading a bunch of data at once. So both Parquet and Arrow are columnar, but they're not the same representation. And that's because they're a different trade-off, right? So when you look at Parquet on disk, the goal is storage. So you will store the data once, and it will be accessed from multiple queries, from different point of views. And so you want to prioritize for I/O reduction, right? So you want good CPU decoding, good CPU efficiency, but you want to compress more, and you want having the ability to access different columns independently becomes really important. And it's mostly streaming access, where we are going to do a lot of scans. When we do in-memory, the data is more transient. So usually you loaded it in memory for some specific purpose, for some analysis. So it's more like write once, read once, and there's less reuse of the same data stored. And there's a lot more priority to CPU throughput, right? Because the I/O is much faster because they're closer to the CPU. You still need good I/O because there's still like some bottlenecks there. But the trade-off is different. And so you want to optimize more for CPU throughput. And you still want to be able to scan the data in memory, but you also have lots of use cases for random access, referring to a value by their index. So having the ability to access something in constant time by their index in the data set is important. So I will start with going in more details on Parquet, and then I'll talk more about Arrow. So Parquet, like Arrow, support nested data structures. It focuses on being a compact format, very efficient to decode. You have type-aware encodings. For example, if you have integer values, and the maximum values can fit on less than 32 bits or 64 bits. We can reduce to the exact number of bits you need and use bit packing techniques. If there's repetition in it, we can use run length encoding to and compress it in a very simple, very efficient way to decode. And you get lots of benefits. So those things also work very well if you sort data sets, for example. And it's optimized for I/O, so focusing on optimizing projection push down, so that's the column pruning when you access only the columns you want, and predicate push down, so you have stats in the file. For example, you can have min max per row group for each column, so that if you're filtering on a given value, it's not between the min and the max for the row group, so you can skip the row group entirely. And so there's several levels of this, and I will go into details. And we've been talking about nested data structures, and my example of tables are flat. But basically, I won't go into details because it takes a little bit of time. I had wrote that blog post that goes into detail of how the nested representation works, borrowed from the Google Dremel paper. And basically, if we want to simplify, if you have a columnar file and you want to store whether a value is null or not, you can use a bit set, so a single bit for each value, is it null or defined. And when you think of a nested data structure, what we're doing is instead of having 0 for null and 1 for define, the definition level is the thing that and we tell you at what level it's defined. So for example, if the document is defined but name is null, it's going to be 0. If name is defined but language is null, in this example, it's going to be 2. If country is defined, then it's going to be 3, right? So it's telling you at what level the null is, and if it's the depth for that particular field, then the field is defined. And same thing for repetitions, the ability to have lists is just a value that tells you at what depth in the tree is a repetition happening. And so that's the general idea, and for the purpose of this presentation, I will keep to simple cases, but you can read that blog post to get details. So to sum up, right, access only the data you need. Projection push down, you narrow down to the columns you want. Predicate push down, you narrow down to as much as possible only the row groups or the pages you want to read, and you minimize I/O, minimize decoding, all those things. And so I'll go in the details of this layout. So you have one Parquet file, it has a footer with metadata about where are all the bits and pieces inside of it. Then it's split in row groups, so each row group is a group of rows in columnar representation. In this row group, the piece of the column that is in the row group is called a column chunk. And so here, we have 4 columns in that data set. And each column chunk is split in pages. And a page is the individual piece of data that is compressed, right? So that's the smallest part of data you can access at once because you need to read an entire page, decompress it, decode it, and access it. And so for each page, there's a header. And so a header is kind of like, hey, what's the size of the page? What's the compression algorithm used to it? What's the encoding algorithm used to encode it? And you have the repetition levels and definition levels. So repetition levels and definition levels are those small integers that store the structure of the record, right? So that's what enables us to have like a flat column representation. And then the structures is captured on the small integers. Is it null? What level is it null? Is it part of a list? At what level is it part of a list? And since those are small integers, we can store them in a very compact way, right? Because if there's no nesting, well, you may need no bits at all, because if it's defined all the time, you don't need any definition level or repetition level. If it's nullable, then you just need 1 bit, and we can bit pack those values. And so there are 2 ways we encode. Look just at the definition level. So you can imagine, well, is this value null or not? So it's 0 or 1s. And so the way we encode it, we have this hybrid model, or we either do bit packing. Basically, if it's null or defined, you just use a single bit to define whether it's defined or null. So that's null, define, null, define, null, define in this example. And for the case where, it's always defined or it's always null, then we can instead switch to a run length encoded based thing, which is run length encoding is just, we have 5,000 zeros. Right? So instead of putting a lot of zeros and 1 bit for each, we would store the number 5,000, then 0, to say there's a lot of zeros. And that's going to be interesting. So that's how we store, the structure, whether the values are null or not. And that's going to be important later. How do we integrate Parquet and Arrow together? So Arrow is slightly different. So some of the Arrow goals, like Parquet, it's well documented and cross-language compatible. So the spec is at the binary representation level. We have, C++ and Java implementations. And so the goal is, the spec is not, don't look at the Java code, right? It's the actual bit-by-bit representation of things. It's designed to take advantage of modern CPUs, paying attention to pipelining and things like that. And it's embeddable, right? It's a library, so you don't really, as a user, you don't use Arrow as a top level, but you use tools that use Arrow inside of them, like Pandas, Spark, Drill. A lot of those projects are using Arrow already. And so one of the key things is it's fast, takes advantage of CPU for high throughput processing, and it's interoperable. So like Parquet, supports nested data structures in a different way because of the way we use memory. And it's designed to maximize CPU throughput, so it's thinking of CPU pipelining, single instruction, multiple data type vectorized instructions, and cache locality in the CPU. And scatter gather I/O, this is the property of Arrow of incurring 0 overhead serialization. Basically, Arrow doesn't need any serialization, deserialization to transfer on the network because the in-memory representation is the same as the wire representation. So all you're doing, scatter gather I/O, is you're just telling the network stack, here are pointers to buffers, copy those buffers to the network. So basically, you have 1 buffer per column. And on the other end, from the incoming network buffer, you can directly read the data, right? The representation coming from the network is already the in-memory representation. So you just have all your column buffers in memory, you can already access them, as opposed to a regular serialization model with objects, and row-oriented records when you have pointers, right? So you have absolute pointers to structures in memory. So you need to translate that into a serialized version. And then when you put it back in memory, again, you need to deserialize, which uses a lot of CPU and a lot of moving around in memory to create new objects and pointing to them. And so the way memory and CPU work, this creates a lot of inefficiencies. And just like doing a lot of small allocations or doing a lot of small copies, when in their Arrow representation, because it's columnar, you can just copy the buffers 1 per column, and that's a lot more efficient. So I mentioned how Arrow is better for pipelining. So that's a quick slide about reminding everybody what pipelining is. So CPUs, the processor doesn't execute 1 instruction at a time. It used to. But today, to make it more efficient, since the CPU has it has a surface area and different areas do different things, it's split into a pipeline. So to execute an instruction, you need to go sequentially to a bunch of steps. And to make things happen faster, the CPU executes the first step of the first instruction, and then it will stagger execution of each instruction, right? So first instruction starts going through, and before it's finished, the next instruction gets started, right? And so if you can parallelize execution and the instructions like that, on average, you increase the throughput. However, if you have any data dependencies between 2 instructions, and you need to wait for the result of the previous instruction before starting the next one, for example, you're jumping on the condition, right? You have an if something, do that, otherwise do that. That means you don't know which instruction you need to execute before the previous one is finished. So that creates what we call bubbles. So here I have an imaginary, 4-step pipeline while showing this instruction moving through the pipeline. And so we lose 3 cycles. But actually, you know, today pipelines are more a dozen or more instructions, steps in the pipeline. So whenever there's a data dependency, you lose a lot of cycles, and the CPU goes a lot slower than it could go. And so to work around this, the CPU has tricks. You know, there's this thing called a branch predictor. So basically, instead of waiting for knowing exactly which instruction to run, the CPU will guess what instruction it is. So you have a if this, do that, or you have a loop, and maybe 400 times do the same thing. So what the CPU will do is pick one branch. For example, if you have a for loop, and you do 100 times the same thing, well, you can just pick, well, I'm just guessing we're going to go up to the beginning of the loop again. And most of the time it's right, and so it's going to start the right instruction and avoid the bubble altogether. And again, we have maximum throughput. And the last time when you reach the end of the loop and you don't start over the same thing, well, it's wrong, but that's okay. Worst case scenario, you just waited the same thing that if you hadn't guessed. So that's become a very important concept of how the CPU tries to go faster, because that will impact how we write code. That means we want to avoid any data dependency, and especially data dependencies that are hard to predict for the processor when we write code. And so that kind of, I mentioned that because that drives some of the design of how Arrow works. So Arrow in-memory representation is fairly simple. So I have some JSON data here as an example, and here's the same data represented in Arrow. And so if we start with this edge column, so basically fixed width column, so we simply have a vector of all the values, right? Maybe they encode it on 4 bytes or 8 bytes, but that's fine. They're all fixed widths, so it's easy to access a value by its index. You just multiply by the width of the value, and you just put them one after the other. For simplicity of this slide, I didn't represent the bits to represent that it's defined or null. So you always have a bit vector that also contains that this thing is defined. Now, if we look at name, name is a variable width value. So basically, in Arrow, it's very similar to the representation of a list of fixed width value. So we have one vector with all the values one after the other. And then there's an offset vector that points to the beginning of each list. Right? So if you have a string, it's the same thing as a list. So you know, it points to the first value, and then the second offset points to the second value. So if you want to know the length of the first value, you just do the difference between the beginning of the next value and the beginning of the current value. And there's always an extra offset for this purpose, right? Because there's like a pointer to the non-existent last, like after last value, so that you can still know the width of the last value. And this offset vector notion, it's composable, right? So for phones, I have a list of strings. Here we consider variable length. So you put all the values one after the other. Then you have a string offset that points to the beginning of each string in that vector. And then you have a second offset vector, which is the beginning of each list inside vector, right? So that's very good composable property. And so that's how you store all the repetition definition of lists in Arrow, and you have a good, that's how you still have a columnar representation when you have all the values one after the other, and that's how you preserve structure. And so when you look at the in-memory representation, you have similar, you know, if you're sending data over the network, you will have a data header, which is like metadata. What is the size of each of the column? What is the type of each of the column? And then you have all the vectors I talked about one after the other, right? So you have the bitmap that defines whether a value if null is defined. You have the offset vectors for the beginning of each string, and you have all the strings one after another. So when you send data, you tell the network, here are pointers to a bunch of buffers, send them to the network. On the other end, the network stack puts them in memory in the incoming buffer from the network, and you can read directly from there. There's no transformation to turn this network representation into the in-memory bunch of pointers, right? So serialization is basically free. You don't spend any CPU time in that. And so now that we understand how Parquet and Arrow works and some of the CPU properties that we want to optimize for, I'm going to go over now how do we make a very efficient Parquet to Arrow reader. So this is side by side the various representations. So that would be adjacent. So I'm taking a very simple example and I leave as an exercise to the reader to extrapolate to all the cases when you have nested data structures. But let's say you have a simple data set. There's one column called V, and you have a bunch of values, A, B, C, and they're single characters for the purpose of this, and sometimes they're null. So in Parquet, since we optimize for compactness, we store only the non-null values, and then we rely on the definition level to know when there's a null or not. So you can start by looking at the definition level. One means it's defined, so the first row is A. Second row is B. Third row is null. Fourth row is C. Fifth row is null. And sixth row is D, right? That's how you read Parquet. For Arrow, since we want also to optimize for absolute constant time access to an index. So the structure I was showing optimized for that, right? So maximum number of hops is proportional to the depth of the schema. So it's bounded, you could consider it constant in terms of the schema. So you have a structure that's very similar, but we leave empty slots for a null value. So basically this value is undefined. You're not supposed to go look at it, right? So you will have a vector if it's defined, this is my first row, this is my second row, third row is null, fourth row is C, fifth row is null, sixth row is D. So in that simple case, it boils down for turning this representation into that one. And so here's a very simple way of doing it, right? You loop through the value, it's what I just did manually. If the definition level is 1, that means it's defined, so we need to set the value. The next value we deserialize at this index, right? So first one is defined. I set A in the first step. And I also, so part of that means I need to set this value to 1. And I set the value to A. And if not, then I skip that value. I'm not setting it and I go to the next one. So there's several inefficiencies to that. So first, if we do the simple, we abstract everything out as if they're values. Now we have to set each bit independently. So the way you set a bit to 1 is you get the byte that contains it. You create a mask to set just that single bit to 1. And then you set the byte back into the vector. So that's a little inefficient. And second, here, those who followed along, you have a big bad data-dependent if in here. Big bad data-dependent jump. So if you remember the pipelining problem, if we have 1, 1, 0, the branch prediction algorithm in the CPU is not going to predict what your net value is going to look like, right? So it's more likely going to take the branch that's most common. That's all it's going to do, right? So, you had 1 twice. So the third time I'm going to go through that as well. Oh, I'm wrong. So here you have a bubble. And then I have 1 again. Maybe I considered, I do the right thing. But then the next time I'm wrong again because it's not the majority case. And so on. So you have a big bad data-dependent block here. So every time you have something that's not defined, you have a big pause in the CPU pipeline. You don't get maximum throughput. So now that's because we base our things on abstraction layers. Anybody sounds Trek? Yeah. Ogres are like onions. And just like software, they have layers. And so really the key to that is to peel away the abstraction layers so that we can do vectorized read. So we need to take advantage of what we saw about the Parquet structure to do a more efficient mechanism. So remember, the way those definition levels are stored, they're bit packed because they change a lot. So we just use a minimum set of bits. We need to store them, and we just put them one after the other. Or they're run length encoded if we have a lot of them of the same type, right? It's defined for a long run, or it's not for a long run. So we can take advantage of that to first compute the indices we need to set, and this can be done with zero branching. So that's the important part. And compute those index, and then we can set those values. Now that we know what values to set, we can set them one after the other with zero branching. So now we get, at the cost of having this internal materialization of those indices, we now have a zero branching loop. So that's very efficient for the CPU because this branch prediction algorithm basically is always right, because we will do, maybe 1,000 times, do that loop, do that loop, do that loop. So 1,000 times it will predict go there. And the last time it will be wrong, but that's negligible. And in the run length encoding case, where really we're going to say, well, 4 values are defined, and then 2 values are undefined, or maybe it's 5,000. So in the case where it's defined, here, if it's defined, then we can set the range of bits at once, right? And setting 8 bits to 1 is just putting the byte with all the ones put together, so you can do that a lot more efficiently. And then again, you have a loop with zero, with no branching in it inside the loop. So you have a tight loop that can be very efficient of setting all the values in the right place. And if the value is not defined, well, we just skip. There's nothing to do, right? We just increment the next slot for the next range of values to set. So this is a lot more efficient, and just by understanding, peeling away the abstraction layer, we can be a lot more efficient. Now you can take advantage of that to do predicate pushdown. So remember the structure of the file, right? So let's say we have a file with 4 columns, and you want to select BCD where A equals 3. And so the naive way to do this is first you take your columns, there's whatever encoding scheme we have, you decode them, now they become values, you apply the filter to A, right? We want A equals 3, so we take the values that correspond to that. Here's your output, ta-da, you're done. However, if you decompose and you look at how things are going, by peeling away the abstraction and not just like relying on, oh, give me the values from the encoding layer, you can do a much better job. So first, each page has a header, and there are some statistics in there, like, for example, min-max value for each column. So we can start by just evaluating the filter. Evaluating the filter would give you the indices of the column you need to read. So first, you can skip pages. Maybe the second page, all the values as greater than 3. So you don't need to decode it to read it from disk. You need to decode it. You don't need to decompress it. You just decode just the pages you want based on that first skipping. And second, you evaluate the filter on just the A column. And so here we decided to use deltas instead. So deltas or indices are the same thing. Deltas is just how many rows to skip until the next value. And so now you can decide to decode BCD and get only, so here we're getting the first row, we're skipping the second row, and getting the third row. So same thing, right? Each page has a certain number of values in it, right? So we can skip the pages we don't need to read, right? So if here we're reading the first and the third row, so we can skip those pages that we don't need because we know this page has enough value for us. So first you skip pages based on the metadata, so you don't need to read it from disk, you don't need to decompress it, you don't need to decode it. Then you can decode and apply the filter at the same time, and the next thing we can know is because the encoding of the pages also can be interesting. We can leverage what we know about the encoding because it could have run length encoding in there as well. We can more efficiently decode selectively what we need and materialize only what we need. So by peeling away the abstraction layer, we can do a much better job. So that the fast Parquet to Arrow decoding and why it's fast. And now I'll spend a little bit of time on talking about the interconnection based on Arrow. So this is an example of work that has been done with Spark and Python. So PySpark used to work using the Python serialization pickle, and so it suffers from the cost of Spark to send data to Python. It needs to generate those objects and serialize them. So there's a lot of looking up in memory and turning to that presentation. Then Python deserializes them, process them, and then reserializes, send them to Spark, and then Spark needs to deserialize and turn into their internal representation. So instead, if you can use Arrow, you remove all the costs of serialization, deserialization. You could just copy the data over. And second, because on the Python side, the Pandas project that is integrating with Arrow, they can do vectorized execution that, a lot of operation, the columnar representation in memory enables algorithms that take advantage of CPU pipelining and better cache locality, or possibly using SIMD instruction. Because the data is laid out, if you want to do the same instruction on a bunch of values that are one after the other, the columnar representation makes that really easy, right? So you can tell the processor, do that same thing over and over, and it's really efficient. So here I'm advocating, there should be like Arrow-based, if we can define a standard for Arrow-based RPC, like give me data, like standardizing what the projection push down and the filters are, and return me in Arrow format, that becomes a new ODBC, It's kind of the standard exchange, and people can directly have efficient exchange of data and, intercoding the system. So the PySpark example, I want a Python function to run really efficiently in Spark that is JVM based, that can be done efficiently. If you want to read data from HBase, Cassandra, Kudu efficiently, you can have that without having to pass through this serialization format and without having to negotiate a different contract every time on how I'm going to efficiently get only the subset of the data I'm interested in. I don't want to scan all the data. I want to filter it, push the filter, push the projection to the storage layer. And so that's how it would look, right? You have a storage layer. You have this notion of filter push down. You can pass it. It does an efficient materialization of those objects, send them to the network with serialization free. And then on the execution side, you can work directly off of the columnar representation. So there's no transformation involved. You don't waste any CPU transforming things, right? So you have a direct integration. The storage layer presents data that is already well suited for in-memory vectorized execution. And from that you could build a cache mechanism, in-memory cache mechanism, or existing cache mechanism could use Arrow as a standard data exchange. And so this is an illustration on how distributed query execution works using Arrow. So simple case, you do scanner, maybe you do a partial aggregation like you're doing a sum. In my case, I'm doing a sum. You prepare each segment that goes to the right machine. That's where a shuffle works, similar to MapReduce, similar any type of aggregation. Then you do the final aggregation in memory on those columns and send the result to the user. So I'll send the slide. Here are some numbers of some integration that have been done. A lot of this is the result of Wes McKinney's work, who's one of the creator of Pandas. A little overview of all the binding. So Parquet has a bunch of language binding and has been integrated in many, many engines. Arrow has a lot of binding. Actually, there have been more that I forgot to add to those slides. And it's getting integrated in several cases. And lately, there's been a lot of interest in the GPU community because they have the exact same problem of how do we exchange data around things. And on that, I have some number of the Arrow release, but it's just showing the activity of the project. And please get involved if you think it's interesting, if you want to put pressure of your favorite project to have better integration so that things work better together and more efficiently, feel free to do so. Thank you. And I have a we are hiring slide that I just leave on. Yeah, so sorry I cannot took into the questions, but oh, no question, please. Sorry? Oh, thank you. Yay! And so if you have questions, I'll be happy to answer to you outside.